Hello, and welcome back to another computer science tutorial video. Last video we covered the absolute basics of computers and how the most basic logic circuits worked in a nutshell. This video we will take a look at what binary and hexadecimal is. So without further ado, let's get right into it. The first form of information I'm going to talk about is binary. And first of all, I'm going to clear up a common misconception. You ready? They are not actually ones or zeros, they are ons and offs. Remember back to my previous video on logic gates. Each 1 or 0 just represents whether the output is on or off. You can even see this in real life objects like electrical toys, which have an on-off switch with a 1 for on and a 0 for off. The reason computers read information through ons and offs is because the only thing they can understand is on or off. Their circuitry is based on it after all. But what do they represent, you ask? Well, each binary number represents a denary number, which is just a basic old number that we humans know and love. And if you can do basic arithmetics and adding 2 or 3 digit numbers, converting between the two should be a breeze. Now, let's actually do it. In this video, I will cover 8-bit binary numbers, and let's first clear up some terminology. Each little placeholder is called a bit, 4 bits is called a nibble, and the whole 8 bits is called a byte. 1000 bytes is called a kilobyte. 1000 kilobytes is called a megabyte, which then goes to giga, tera, peta, and so forth. Each bit represents a denary number, which going from right to left is 1, 2, 4, 8, 16, 32, and so on until it reaches 128. Basically the previous number just keeps getting times with 2. Each bit underneath the number represents whether it is on or off. So for example, the binary number 10000001. We can see that the 128 is on, and the 1 is on. The rest are not. And all we have to do now is just add up all the numbers which are on, making that binary number equal to 129. Now that's pod racing. Converting binary numbers to denary is actually pretty easy. All you are doing is simple adding. Converting the other way, however, is a bit more hard but still relatively easy. Let's have our example number as 71. To convert from denary to binary, we should work our way from left to right, adding the current number and checking if the total is bigger than a denary number. Okay, let's do this. First bit, 128. Is that bigger than 71? Yes, therefore we keep it as 0. Next bit, 64. Is it bigger than 71? No, so we put it as 1. Next bit, 32. Since we have 64 as 1, we have to check by adding the next bit to all the bits that are on. 64 plus 32 is now 6. Is that bigger than 71? Yes, so therefore we keep 32 as 0. And you keep doing this until you get right to the last bit and you're done. From this we should have 01000111. We can check this by adding up all the bits. 64 plus 4 plus 2 plus 1 does equal to 71. We have successfully converted from denary to binary. Isn't that great? You can also figure out whether a number is odd or even by looking at the last bit. If 1 is on, then it must be odd, and vice versa. Now I will show you how to add 2 binary numbers together, which should be pretty simple as you're just adding 1s and 0s. If you went to school, you should be familiar with the column method. Binary adding pretty much uses the same technique. Let's for example add 00110101, which is 53, and 00110110, which is 54. We put the two numbers over each other into a column, just like so. Now before we start, let me clear up a few things. 1 plus 1 is 10, and 1 plus 1 plus 1 is 11. This will make sense later on. Okay, so let's do this. We now work from right to left. Okay, 1 plus 0, that's 1. So 1 now goes into this bit. Next bit. 1 plus 0, that is also 1. So 1 goes into this bit. Next bit. Now you might think that 1 plus 1 is 2, right? Well, you're wrong. Think back to what I said earlier. When adding binary numbers, 1 plus 1 is 10. So this bit becomes 0, and the other 1 carries over to the next bit. 0 plus 0 is 0, so nothing changes in this bit. In the next bit, we have 2 1s once again, so it is 10. But wait, the extra 1 carries over to the next bit, which also has 2 1s. Once again, like I said earlier, 1 plus 1 plus 1 is 11, so these 2 bits become 11. And the final outcome should be 01101011, or 107. We can check if our answer is correct by converting the binary numbers into denary and then adding them arithmetically. So, if we convert our numbers, they would be 53 and 54. Add the two together and we get 107, which is our correct answer. Another thing they can do is times and divide them. which is even simpler. Well, only if you're planning to times and divide by 2, since all binary is basically just all the exponents of 2. To times by 2, all you have to do is shift the numbers to the left, for division to the right. Now you might be wondering, what happens if I shift the 128 to the left? There aren't any more bits there. Well, this is something called an overflow. An overflow is an error when the computer handles a number outside of its range of bits. For example, an 8-bit number, such as the one we are using now, can only represent numbers from 0 to 255. 128 times 2 would be 256, and thus the bit will just disappear and give 0. Having an overflow doesn't exactly mean that the software is going to crash. It will only give the wrong result. Now that's it for binary, time for some hexadecimal. Hexadecimal is easy to grasp if you already know how binary works, so this should be a breeze for us. Hexadecimal is a base 16 form of information, unlike binary, which is base 2, meaning that there's only 2 ways to represent information. Hexadecimal has 16, so let's go through all of them. First of all, we have the numbers 0 to 9, which are represented by 0 to 9. And then 10 to 15 are represented by A to F, which is shown on the screen. Each hexadecimal number will have 2 parts, for example, A4 or FF. Each part is a nibble, and both of them together is a byte. So let's begin a conversion. Let's convert the binary number 10101111 into hexadecimal. First things first, since each letter in a hexadecimal number represents a nibble, let's break apart our number into 2 nibbles. Now think of these as 2 separate numbers from now on. Now we can convert each nibble into a denary. 1010 becomes 10, and 1111 becomes 15. Now look back to our previous chart to convert each number into a letter. As you can see, 10 equals A and 15 equals F, making 10101111 AF. Easy! AF. Now where is hexadecimal used? One of its primary uses is for representing color on your screen. Let's take a look at how that works. Remember the primary colors I taught you in art? Forget that. Don't trust people who cut their own ear off. The red, yellow and blue model only applies to paint. In reality, our eyes can only see red, green and blue. That is humans, of course. Some animals can see more or less colors. Some even ultraviolet. Anyway, back to my point. Since our eye only has 3 cones, one for red, one for green and one for blue, each pixel on a computer screen therefore has the ability to toggle how much red, green or blue it can show, resulting in all the different colors on your screen. Now this is where hexadecimal plays a role. RGB can be represented with 3 numbers each ranging from 0, no color, to 255, maximum color, with a number for all 3 colors. For example, 25500 is bright red, 02550 is green, and 0255255 is cyan. Since each color can hold a maximum of 255, we can tell that it is a byte per color, and one hexadecimal number is equal to a byte. For example, let's represent cyan in hexadecimal. Our numbers were 0, 255, 255. Now all we have to do is convert each number into hex. Our first number is 0, in hex, 00. Our next number is 255, in hex, FF. So 0, 255, 255 in hexadecimal would be 00 and then 4 Fs. So that's it for binary and hexadecimal. I hope that you all have enjoyed this video, and if you did, remember to like this video, subscribe and hit the bell button so you get a notification for my next video, which is computer hardware. So with all that, peace out.